So gradient of matrix with respect to matrix. So now we have a matrix in input and we have another matrix in output. So what's the rule? F is mapping from n by n matrix to n by n matrix. And so let me change m to this. Okay. So okay, so what's the computation? So we have n by n matrix R. So here the notation is so we are sticking to the notation of the book, but now R we are not going to use it in bold because now the bold is really similar to that the set of real numbers. So we're just gonna make it non-bold. So R is mapped to R transpose R. We have a n by n matrix. Now R transpose R is once again a pairwise inner product between columns. Okay, so it's going to be n by n. So we denote the output as cap K in bold. So R transpose R. Now we think, okay, the output is R transpose R. The input is the matrix R. What's going to be the Jacobian? Okay, what's going to be the derivative? Find dk dr. So now, firstly, we figure out the dimension of the tensor. So always dk. So the output is k as a square matrix n by n. So we want to preserve the format of the. We want to preserve the data structure of the output, the format of the output. And now for every input we have n by n matrix, and we have n by n of the arguments. Okay, so n by n goes to the second and the third dimension. Now consider. So for the matrix multiplication, it's R transpose R, right? So we have so every element of cap K is computed in a slightly different way. So consider cap K PQ differentiated with respect to the input matrix R. So this is 1 by n by n. Okay, so just picking one component of the output. Okay, for all PQ between 1 and n. All right. All right. So now KPQ, how is it computed? KPQ equals to. So it's R transpose R, right? So we want to look for the pth row qth column entry of the product. So it's gonna be the pth row of R transpose multiplying by the qth column of R. Okay. So realize that the row P of the R transpose is actually the column P of R holding transpose times column Q of R. Okay. And now we see, okay, essentially, if you are looking at the pth row qth column of the pairwise inner product, it's going to be the pth column dotted with the qth column. Okay. So now if we write it everything in terms of a sum, so this is we have what we have. Every vector is m dimensional. So this is k from 1 through m. R. So since the column index is P or Q, so it's going to be KP and KQ. All right. So each of these vectors, they are Rm. Rm. So really similar from before, because before it's AX, it's matrix multiplication. Here, this is R transpose R. It's a similar matrix multiplication. Now, what do we see here? We see basically the K index the first index of each term is from 1 through m. It covers everything. But only the second index is about the columns that are fixes P and Q. Okay. All right. Now, computation. So for the Jacobi determinant of the entry PQIJ, so here we're going to stick with PQ for the the output indexing. Okay, IJ is going to be the input. So P is from. Let me also put down the lower upper bound so that everything is somehow we keep track of the things. Okay, so P and Q and J, they're all upper bounded by cap n, but the I is upper bounded by cap m. This is del K PQ del R IJ. Okay, so now we're doing the partial. We're doing the partial of the ith row jth entry of the matrix R. And just look, so these are right hand, so these are PQ, KPQ. These are also just you can say it's a polynomial in terms of the entries of R. All right. So we can write it as it's a partial of a sum, right? It's a sum of partials, which we can write out. So this is del Rij del of RKP RKQ. All right. So here, what can we say about the sum? So remember, this is the element at the ith row, jth entry. Okay. How about these? K, the index goes from 1 through m. So if the index K is different from I, we are definitely not in the same row. Right? So Ij is the ith row element. So if your K is different from I, let's say you have 1, so R1P times R1Q. Differentiating with respect to R2J. They are not related at all, so the derivative is just going to be a 0. Okay? Only when K is I, you will have something reasonable. Okay? So if you throw away those obvious zeros, it's going to be just del Rij of RIP RIQ. All right. All right. So here we have one term, two R expressions multiplied. So it's a product, right? So it equals to the product is the product rule. So the derivative of the first, the partial derivative of the first, so it's RIP, multiplying by the second IQ, plus the first RIP times the partial derivative of the second. All right. And now we see at this point we have an indicator again. Since each Rij, RIP, RIQ, they are possibly distinct entries of R, of matrix R. Only when they have the exact same index will you get a partial derivative 1. Okay. So only when P equals to J will this give you a 1. Otherwise, it just give you a 0. Okay, so this is again checking the index, checking the indices, and it's checking the second index. So this is identity if of P equals J, okay, RIQ, plus here. Let me write out the indicator again. So here the second fraction, the second partial is only 1 when Q equals J. Okay, RIP. So now you see we have a sum. So if you treat each term as a tensor that you can construct, then this is actually a sum of 2 tensors. So now just realize that this is a four-dimensional object, so it's clearly not easy to visualize. But what we can say here, you can see P, Q, and J, they all have the same dimension n, right? So this is saying, well, this is saying, okay, if I fix I and Q, if I let P and J run through, then this is actually a slice as an identity again. Okay, so I keep. Okay, so for this one, so let's call this key, let's call this T. It's a tensor. T where we specify J and Q. So J and Q is let P and J be free. Okay. Q and I and Q. Q is here. I is here. J is here. So I fix I fix Q and I, the second and third index. So this tensor here equals to identity. IN, PQ are from P and J, that's n dimensional, times RIQ. Right. And for this one, it's similar. So this let's call this T prime. So it's not really a derivative. But now I have I and P to be specified. So P and I are specified. P colon I colon is a slice where we fix P and I. This becomes again identity of n-dimensional multiplying by the number RIP. Okay. So you fix two arguments, you have identity in a sense. And now these are two tensors combined. So each one of them has a relatively simple structure. But now you're just adding two up. And of course, for tensor addition, it's really similar to matrix and vector addition. That's component-wise. Okay. So definitely, it's not a simple geometry, but you get an idea. Right? And I think in the book they do have a different way to put down the final result, but it's essentially the same thing. Okay, so any questions? So yeah, this is a relatively tedious process that you need to compute the thing to the end. Okay, so for explicit expressions. But to the intuitive way here to define your tensor is just by each component, okay, which is essentially not so bad if you go over more examples. So so let's continue with 5.5. 5.5. I think we need another page. So let's jump into 5.5. There's another page. So 5.5 is a section that's relatively short in the book. However, it's relatively I would say not that straightforward. Okay, so let's do that. Useful identities for computing gradients or derivatives. Okay, so here it's not really straightforward because now for matrix outputs, okay, or matrix inputs, it's easy that you get a tensor for the gradients for the Jacobians. However, when you talk about certain rules of matrices, they are not going to be exactly the same as before in the tensor format. Okay, so now for mapping F that maps X to F, where we have input to be a matrix that's P by Q, and the output is a matrix that's M by N. Here the rule is the following: so del X of F of X holding transpose equals to So here the notation is del x. It looks like a partial derivative, but it's the same thing if you write it as d. Okay, so it's just the Jacobian matrix that is specified. So this equals to del f del x whole thing taking the derivative. So here, very important, this transpose is on the first two dimensions. Yeah, let me erase it. First two dimensions of the tensor. So what do we mean? So here, if you think about f of x, right, this is mapping an input x, p by q matrix to an output of n by n matrix. So when you do the transpose of the final result, it's going to be a matrix that's n by n. All right. So now this is the matrix output. So here, this thing is this n by m output. You do the partial derivative. You do the gradient. This is n by m by p by q. All right. So here this is the transposed out matrix output, and then you are doing the derivative. Okay, so this is n by n by p by q. But now if you look at del f del x, this is the result here is n by n because the output of little f is n by n, and now you do the tensor, you do the Jacobian tensor is the p by q afterwards. So you notice if you compare the left hand side and the right hand side, this transpose looks to be swapping these two dimensions. Otherwise, it doesn't make sense, right? And this equation tells you what? The equation tells you, okay, now if I do the transpose of the output, then what happens is that now the resulted four-dimensional tensor, you need to do the transpose on the first two dimensions to get the new result. Okay. So now let's quickly do a short proof. So this is relatively simple that we can do through definition. So just think about for each of these partials. So basically we have a matrix output of n by n, right? So if you look at every entry, it's going to be a scalar. So for partial derivative of f sub ij, taking the partial with respect to the entire matrix input, so this is going to be 1 by p by q. Okay, so it's a scalar, right? So for every pair ij, it's going to be a scalar output, and then the domain has well, the preimage is p by q matrix, so it's 1 by p by q, and then essentially for the left hand side for this transpose matrix, then every element is going to be somehow related to Fij. So and of course here let me add one more one so that so essentially we somehow we fix the first two dimensions. This dimension is I chosen to be I. This dimension the index is chosen to be j, right? And then the last two they're about the input x where they're free, right? So now let's look at the left hand side of the equation. So the left hand side, this is for all ij, I from 1 through m, j from 1 through n. Okay. All right. So now the left hand side. So now for F transpose. So here I'm just omitting the argument x. Okay. So basically F is the output matrix. That's n by n. Now I take the transpose. So here, if I want to put all the things together in the tensor, I just need to basically just get all the arguments, and then I'm gonna stack. So get all the entries of the matrix, and then do the partial, and then I'm gonna stack all them together. So here this is let me choose the element, this ij, and then this is the scalar output again, and then I'm gonna take the partial derivative. Okay, so here this is the same dimension, but then to construct the left-hand side, I just need to go over all the ij pairs, and then I stack them up. Right? In the corresponding manner, this is the correct manner. All right. So now what's this? So F transpose ij is actually saying, okay, I have F transpose. I'm taking the ith row, j's column. That's the element is the same thing as Fji. Right? So this is exactly Fji. I'm taking the partial. So this is basically that scalar is exactly this. So now you see, okay, now here I'm stacking I first and then J. So that's exactly the transpose of the first two coordinates, excuse me, of the first two dimensions of the four-dimensional tensor that I have on the right-hand side. So this is what this is exactly. So if you think about this, this is the tensor right here. I've swapped the first two coordinates, and then I go ij for the first two indices, and then colon for the just run through the third and fourth dimensions. Right? And basically, if I want to construct the left hand side, then this is collate I and j. So I going from I goes from one. So firstly j is one, and I goes from one through n m, and then j equal to 2, I goes from 1 through m, and all the way down. Okay. And here for this side, this is the same thing. I'm also running increasing I first and then j. Okay. So that's done. So basically, so this gives you an idea of how to show this kind of identity for tensors. Basically, now you say, okay, I have two tensors. Here, if so, there are a few ways. So this is saying, okay, if I choose ij, if I choose the first two indices as I and j from here, that's going to give you a slice. If that slice is exactly the same as the slice that you choose on this side, and then now for all ij's, slices is the same thing, so they're essentially the same. Okay. And of course, if you say, okay, I have two tensors, I do the ijkl element, and that match with the ijkl element from here, they're also the same for all ijkl. Then that's also saying that the tensors are identical. Okay, so they're really similar to matrices, but now it just have more dimensions. Okay. All right, so let's look at the ones with symmetric outputs. Okay, so let's say we have f of x that maps from P by Q dimensional matrices to M by N square matrices. So now here, I want to do the partial with respect to the matrix input x of the trace of f of x. Okay, so if you look at the homework from that I just assigned from today, there's a trace of a matrix that I need to compute the gradient. Okay, so that's something related to this. So here, once again, f of x is a square matrix, so the trace is just taking the diagonal entries, right? But now this is a scalar function, so it's a scalar function. So here is the Jacobian. So one is the dimension of your output, and then x is p by q. So essentially, you have a p by q matrix, right? But now the right hand side, if you look at the right hand side, it's a trace of the Jacobian tensor. But now here, the equation is like this. But now here, I want to highlight that the trace here is with respect to the first two dimensions. Okay. So trace, just like the previous equation, trace on first two dimensions of the tensor. Because if you think about the thing here, like what we have seen before, so f has an output that's n by n, and the input is p by q. So del f del x is a four-dimensional tensor. Okay? So, but here when you talk about trace, that only makes sense if you're only looking at the first two indices. Okay, right. So and this is actually not so difficult. Still by definition. Okay, so let's look at this. So here, let's again abbreviate the argument. So this is the trace of f, right? So now the trace of f, what do we know? So the trace is exactly just summing up the diagonal elements. So let's use index a. So here, let's say FAA is the element on the eighth row, eighth column, and A goes from 1 through n. So we have n by n square matrix, right? So that's the trace. And now here I'm doing the partial with respect to the entire argument x. And of course, now the partial derivative of a sum of functions is of course the sum of all partials. Right? And now just notice this thing is exactly, you can say, okay, I can pick up the slice on the four-dimensional tensor by doing what? By picking up my first index and second index to be A at the same time. Right? So that's exactly what it means by saying I do the trace on the first two dimensions of the tensor. Because here, this is exactly A from 1 through n. So this is del f del x choosing a colon running through the third and fourth dimensions. So that's exactly doing the trace on the first two dimensions. So here is well, in terms of definition, it's not so bad. And also when we talk about the geometric, well, 3D illustration, it's also a similar thing. So I'm just gonna do it. Okay. So basically, let's construct the four-dimensional tensor like right below. Okay. So when we talk about the indices, so if you say I have I, J, K, L as indices, so I is the vertical one, J is the horizontal one, K is the frontal, and finally I have this is L. Okay. So the vertical again, all right? So what's going on? So when you talk about summing up the first two indices, you're actually summing up ij, where I and j, the I equal to j, and they run through the square, right? So here every such square is this square and the slice at the back, and even further all the way down at the end, they are what? They're actually just f taking the partial with respect to each xij. So these are what? These are with respect to each x x 1 1 2 1 all the way through x p1. All right. That's now looking at like the first column, but it's let me give the bound. So I is between 1 and n. J is also between 1 and n. K is between 1 and p. And L is between 1 and q. Right? Okay, so now makes sense. So now what about the trace that's taken on the first two dimensions? That's just I and j. So I'm summing up here for the first frontal slice. I'm summing up the diagonal, and then for the second, I'm doing that also. That will give you another number, and all the way down to the last slice. Okay. So this gives me actually the first column of my resulting matrix. So it's basically you see that K goes from the front. So the first slice, second slice, all the way down to the P slice. That's actually giving me the first column of this matrix here. Okay. And then it repeats for the next rectangle all the way down. So the last rectangle, you also do on the first two dimensions, do the trace, and then the next one, and then the next one, and then finally the last one. Okay, so that's forming you the last column of the matrix of the left hand side. So that's doing the yeah. So there will be p times q many diagonals. So those traces will give you p by q values. Okay, so that's what it means by saying I'm taking the trace along the first two dimensions. Yeah. All right. Okay. So now the next one. So any questions before we move on?
Are we always fixing dimensions past the first two, or is it just like the case?
For the equations that are coming up, so these ones with x, indeed, that's true.
Okay.
Yeah. So you have f of x, right? F is the output. So you're doing the derivative of the output with respect to the input. So the output here begins in the first two dimensions, and then the operations are indeed with the first two dimensions.
Oh, right.
Yeah.
For mapping to a square. Okay.
Yeah. So yeah, this is a very good question because let's see, we have two more, and yeah, these are really highly related to the ones we have seen. So now the same condition. So for f of x maps from p by q matrices to n by n matrices, square matrix. We want to calculate the partial derivative of the determinant of the output. So now this is more complicated. So earlier that's the trace. Now the determinant is a little bit more complicated than before. So, but this is still the same thing. So it's 1 by p by q, right? So determinant of the square matrix is a scalar. So the Jacobian is just going to be a p by q matrix. But now the right hand side, this let me write it down. So it's going to be, well, in the book it's written as follows: the determinant again, which is a scalar, multiplying by the trace of f of x inverse del f del x. So this is in a sense more complicated than before, because now if you look at this is n by n object, right? So f is an n by n is a square matrix. F inverse is the inverse matrix of n by n matrix. So it's still n by n. And now, so del f del x is this one. It's n by n by p by q as before. So you do realize what do I have? I have a square matrix multiplying by a tensor on the left. So here, this multiplication is also done in the first two dimensions. So you should see that tensor right above. So the frontal slices are all squares. So essentially, you have F inverse as a square matrix and multiply on the left hand side. Okay, like this, a square. That's the inverse. You multiply. So you multiply through all these slices. That's giving you still n by p by q tensor. Then do the trace along the first two dimensions. So here, trace and matrix multiplication on the first two dimensions again. All right, similar to before, but now we have something even more complicated. We have a matrix multiplying by a tensor. Okay, still on the first two dimensions. Okay. So once you do the trace, that will be 1 by p by q, and then the determinant is still a scalar, so you multiply that. All right. So the proof here is going to be a little bit longer, but still we are doing things sort of by definition. Okay. So now firstly we're going to utilize, so the left hand side we're going to start by doing a chain rule, but here realize that whenever you do the chain rule, the multiplication has to make sense. So here we do the following. So just so determinant of f, right? F is the output. So here I'm thinking about the intermediate variables as every element of my output matrix. So F11 all the way through Fnn. So it's going to be a chain rule. So del x determinant of f, this equals to del determinant of f. So it's going to be a summation. Yes, it's going to be a summation. It's going to be a double summation. So basically, I'm doing, so each chain is f little fij, okay, del fij del x. Okay, so here I and j just go through from 1 through n. So basically, if you want to construct that the tree diagram, that's doing what? That's the determinant of f relies on all the entries f11 all the way down to fnn, and now everyone relies on x. Okay, so that's really a huge tree. But this is so there will be n squared those intermediate variables f's. Okay, so that's the diagram over there. Yeah, let me keep the diagram there. Okay, so this is, so now once again, so now here we do this because this chain rule makes sense. We have a scalar on the top, a scalar on the bottom, so this is just a scalar function. And here this is a matrix. So essentially we have a summation of n square matrices all together. Okay? And now let's look at the determinant. The first partial derivative right here. So what's this? So del of the determinant of the output, taking the partial derivative with respect to the ith row jth column entry of my matrix of my output. So that's going to be what? So when you're doing the partial, you're saying, okay, for the entire square matrix F, I'm only changing the ith row jth column entry, but nothing else. Right? So here I can isolate the effects of my Fij just by doing the Laplace expansion along the ith row. So Fij is on the ith row, right? So I look at that, and then Fij times the cofactor, and then so in the cofactor everything is not changed. Nothing is changed. So this is del Fij summation. So summation. So here let me do the index A from 1 through n. So I have FIA, the ith row, okay, FIA CI. So I'm just rewriting the determinant. So this is a plus. Ith row. And of course, what's CIA? CIA is exactly the cofactor, right? IA cofactor. So, and of course, if you want to write out the expression, it's going to be -1 to the I plus A, and then determinant of the minor, IA minor, removing the ith row and the eighth column, right? But here I'm writing things out because once again, Fij is changing in your in the partial derivative calculation. Nothing else is changing. So these things. So I remove the ith row and eighth column. So the ith row is already eliminated. So these things circled, they are definitely not changing. Okay. So CIA, they are not changing at all. And now, of course, for the ith row eighth column element, it will give you a 0 as a partial when A is not J. Right? So this only equals to Cij. Only when A equals J gives you a 1 for F from right here. Okay. So basically, in the summation, these things do not change because only Fij is changing. Everything else is fixed. Okay. And Fij now is then for the illustration. Square matrix, right? So my ij element is possibly here. And here I'm running through the ith row. Okay. Only the circled element is changing, and I'm doing the expansion along this row. So for all the prior entries, it will give you zeros as partials. Only at the circled place you will get a 1 as a partial. Okay. And of course, those minors that you cancel out, let's say for this entry, you remove this column, this row. So all the minor is not changing at all. Okay. All right. So that's Cij. Now, what's Cij? So recall. So the aggregate matrix of F is Cji. So if you remember when we do the aggregate, what do we know? We know F times the aggregate matrix, a row times a column, right? Equals to determinant of F times identity. So this is the identity that's it's relatively important here. Okay. So basically, it says, well, this is okay for the entire ith row. F11 F so yeah, so probably I don't really have to explain too much in detail, but basically, if you go back to the definition of the aggregate matrix that we slightly mentioned at the beginning of the semester, you realize that okay, for the cofactors, you need to swap the indices to form the aggregate matrix. Okay, so this is actually so the aggregate matrix of F, taking the jth row i's column element. All right. So now we calculated the this part. Okay. So now let's do a summation. So let's take the summation where I going from 1 through n of the chain rule. Okay. So we sum over I first. So now this summation becomes Cij times del Fij del x. Okay. So now realize I'm taking the sum where I goes from 1 through n, and once again notice that the second entry j is fixed, right? So and the second entry j here correspond to the row index of my aggregate, right? The j is actually j is the row index for the aggregate matrix. So let me write it down. So it's the row j of aggregate matrix F multiplying. So here for F of ij, so once again, I is changing, j is fixed. Okay. So when j is fixed, the second entry is so the second index is fixed. That's actually the j's column of, you can say del F del x. But now it's a tensor, so it's actually what? It's actually del F del x. I let I run through j fixed, but finally I have the last two indices running through also. So this is like a slice. Okay. So in a sense, you can think about the second thing as the j's column. So now you have actually a matrix multiplication. You have a row times a column. So that's exactly so row j, column j, right? So that's actually the j's row, j's column element of the product. Okay. So this is aggregate of F times the tensor. Now I'm taking the jth row, jth column element. Okay. Just thinking about the product as a sort of like a matrix. So row of the left matrix and the column of the right matrix. J's row, j's column. Okay. All right. So now realize that we have one more summation. Okay. Upon this summation, we get what we want. Okay. The summation over j. The summation over j. So notice that the black thing is the j's row, j's column element. And now I'm summing over j. That's the trace. This is the trace of my multiplied tensor. This is definitely not trivial, but once we are at this point, we are done. So because if you think about yeah, let's summarize what we have established. So we started with the determinant of F, the determinant of the output. Okay. So now we rewrote the chain rule, and then we now rewrote the double summation as the trace of the aggregate multiplying by the order 4 tensor, right? So realize that aggregate is following this property. Okay, so the aggregate, if your f is invertible, then aggregate of f equals to determinant times f inverse, right? So, and now the determinant you can take it out of the trace. So this equals to the determinant of f multiplying by the trace times f inverse times the tensor. Okay. So this is the inverse matrix of f if f is invertible. So here I would like to quickly mention that this equation is always true. Okay, so that's what we have proved from the red line right above. But then, of course, the aggregate matrix is kind of complicated. So that's why some people they just take out the determinant and just they rewrite the aggregate matrix as F inverse times determinant, and then they take the determinant out. And then of course, since you are differentiating the determinant, then if you still get the determinant expression out, that's probably nicer for the expression, okay, for the meaning of the expression. Yeah. Okay, so question. Yeah, so yeah, well, this one is definitely longer than before, and this is actually the longest proof that we do in this section. But basically, we will see a little bit more, so that you will be more familiarized with this kind of stuff. But now, what's going on here? So F inverse multiplied on the left. That's exactly what I just mentioned. So you have F inverse as a square matrix, right? Right, or aggregate, whatever. So this is n by n. Okay, so n by n. So basically, for the entire tensor, you have this matrix multiplying by every slice, every slice, every slice, every slice, every slice. And then that forms you the new tensor that's of the same dimension. And then you do the trace. Okay. So everything is done within the first two arguments, within the first two dimensions of the product. All right. Determinant. The next one. Now, this is the same setup. Okay, so maps from P by Q matrices X to M by M matrix F, and this time we have a tensor that's constructed from the inverse matrix of F, okay, of the output. So now this is a tensor. Okay. So remember, F is n by n. So F inverse, the inverse matrix is also n by n. So this is n by n by P by Q. So the same dimension as the del F del X, right? But now the equation is the following: is negative F of X inverse multiplying del F del X multiplied by F of X inverse. Okay. Now this looks even weirder. Okay, but now we have seen something like before, then this is not so bad. So once again, F inverse is n by n. F inverse on the right is n by n. now we have seen before that del f del x is n by n by p by q. So you can suspect that it means this matrix multiplication is onto the first two dimensions of the tensor in the middle, and this is a right multiplication to that same thing. So if you go a little bit to the above, the image, so basically that f inverse is multiplied here and here for every slice. Okay, so left multiplication, the right multiplication for every slice, that's resulting in the tensor on the right hand side. Okay, make sense? Yeah, this is definitely something very new. So if you have any questions, just let me know. So here, this matrix multiplication on first two dimensions of the tensor. Okay. All right. Oh, yeah, these equations have numbers that's related to the book. So this is 5.102. The one before is 101 and 190. So yeah, this is 5.101. This one is 5.100. This is 5. Yeah, this is 99. Okay, good. So that you guys will be able to refer to the book conveniently. All right. So here, what do we do? So now everything is in terms of matrices. So it's not going to be easy if we do the partial with respect to the entire matrix X. Okay. So now let's begin with the identity IN equals to F times F inverse. Okay. And now let's do the partial with respect to let's say Xij. So if you do the partial on both sides, with respect to every Xij, what do you get? So for you get a 0 for the left hand side, which equals to del Xij of In, right? And now the right hand side is del Xij F inverse. Okay, I have a matrix multiplication, right? And now what do I have? I have a matrix multiplication as a product. So of course, for matrix multiplication, I cannot really swap the order of multiplication. But now when you do the partial, it's still gonna follow the product rule. Okay? The partial of the first times the second, this first times the partial of the second, without changing the order of the multiplication. Okay, so it's gonna be del f del xi del f del xij f inverse plus f times del f inverse del xij. Right? Make sense? And we're getting there. Okay. So what do we want? We want the partial of f inverse from the left hand side on the top. And then we just need to solve for this, right? So we have f times del f inverse del xij equals to, so basically just subtracting the other term on both sides. So this is negative del f del xij. Just remember each of these terms are each of these terms is a square matrix. Okay, so f inverse the partial derivative and the partial derivative, because although we are taking the partial with respect to one variable, but the output of f and f inverse are both squares. Okay, so then now multiply both sides by f inverse, we will get we almost have what we want. So del F del Xij equals to negative F inverse del F del Xij F inverse. Okay. So now if you look at the equation right here, it's almost as what we wanted. Right? So this is actually that tensor. I'm doing the part. So this is the tensor where I have a slice that's fixing the third and the fourth indices to be INJ. Okay, and this is exactly the same slice with the third index I and last index J. Okay. So if I want to construct del F del X, this is running through the first two dimensions because the first two dimensions relate to the output, right? Wait, that's inverse. F inverse IJ. And this part is del F del X running through the first two indices IJ. Okay. And now if you think about constructing these two tensors in red, what do? You just collate the third index I and the last index J. Okay. And then here for del F del X, when you construct that, you also collate with respect to I and J, the third and fourth indices. Okay. So essentially what you see here is exactly what we just mentioned in that illustration. So that tensor you have all the a bunch of rectangles. So the frontal slices they're all squares. So here we multiply F inverse on the left of each slice. We multiply F inverse on the right of each slice, and then we do that through all the slices. Okay, and with that. Okay. So yeah, these 1, 2, 3, yeah, these four are related to matrix outputs. Okay, we have f of x as a matrix, so the derivative easily gets to a tensor. Okay, and now let's look at something other than a matrix output. So I have A and B are fixed n-dimensional vectors. X is n by n as a matrix. So A transpose X inverse B, taking the partial with respect to X. Okay. This equals to negative X inverse transpose AB transpose X inverse transpose. Okay. So this one is somehow highly related to the previous equation. We have what? We have X transpose X inverse B. So what's this? So just notice that A and B, they're all n-dimensional. Okay. So A transpose is 1 by n. Yeah, let me put it. Yeah, okay, it's fine. A transpose is 1 by n. X inverse is n by n. B is n by 1. So the top, this A transpose X inverse B is actually a scalar. Okay. So you are doing the partial derivative of scalar with respect to a matrix X that's n by n. So this is 1 by n by n. Okay, which is a matrix. And of course, for the left hand side, this is n by n. This is rank 1 n by n matrix, right? So this is like UV transpose for SVD. So this is the column vector multiplied by row vector, that's n by n also. And finally, this is n by n. So you have 3 n by n matrices multiplied. So that's that one, n by n. All right. So how do we play with this? So since the matrices, right, then we just say, okay, for the left hand side matrix and the right hand side matrix, I just compute the ith row jth column element, and then I match. If they match with all I and j, and then I'm done. So this for matrix is always easier. So let's just do del A transpose X inverse B, and I do the partial result to Xij. Okay. So now, here the first trick that I do is I take the trace of that scalar. Okay? I have a scalar that equals to the trace of that scalar, because the scalar is just one by one matrix, right? And now once I have the trace, I can swap the that's what is called the cyclic permutation or something. So it's the trace of AB equals to the trace of BA. Right, so that's something you know. As long as A times B is a square, you can swap the order. You can put the first at the end. Right? So this equals to del Xij of the trace of X inverse B A transpose. Okay. Now I swap A transpose, the row vector at the end. Okay. And now the trace is actually a sum. Okay. So one of the previous equation tells you that you can take the trace out and do the partial derivative on the inside. Okay. So just now you realize that, okay, I have X inverse is an n by n matrix, BA transpose is an n by n matrix. So in the bracket I have n by n matrix. Now the partial is still a matrix, so I to take the trace after I do the partial. And now what do I do? So I have a product, but now I do realize that the product, this part is constant. So BA transpose doesn't change. Okay. So I have a product, and the second part doesn't change. So the partial only does to the first part, X inverse del X inverse del Xj, multiplying by BA transpose. All right. And now I'm at the point where I can utilize the previous result. So what do I have from this equation? Okay, so now I want the partial of X inverse. Okay, so here my function little f is just X. So if that's the case, then utilize this equation right here. I have the trace of, so let me see. I have negative, so little f is X, right? X inverse del X del Xij, X inverse, and now B A transpose. Okay. Okay. So just utilizing that partial that's so-called. Okay. So my F is exactly the identity mapping. So F of X is just X. All right. And here I can utilize the similar trick as before. So the first matrix I put it at the end. Okay. So if you look at the format, is indeed getting close to what we want. So we want something like X inverse some matrix, then X inverse, right? And indeed we're getting there. So we pull out the negative sign. And for the trace, I swap the first block at the end. So I have del X del Xij, X inverse B A transpose X inverse. Okay, and we're almost done. And now, any questions? So here del x del xij. So that's what that's saying. Okay, my entire matrix acts as the output, and then here I'm taking the partial with respect to only the ith row jth column element, only that entry. So remember, if you're doing the partial derivative, every other variable is fixed as constants. So essentially, you have the entire matrix is a constant, and only the ij element is changing. And now you're differentiating on that entry. So that's going to give you one only at that place. So this is exactly the negative sign trace. So this is Eij. Okay. So the matrix having only one at the ith row jth column, and then copying the things down. All right. And now I can rewrite the trace as sum. So the trace is taking okay, I have A and B. So let me pick a C as the index. C going from 1 through n. The element, the C row, the C's row, C's column element of the product right here. So now let me choose the product to be Eij multiplying by the rest. Okay. So now I have the C's row, C's column element in the product, right? So let's say I pick up the C's row of the left-hand matrix and the C's column of the right-hand matrix. So this is row C of Eij, column C of what's left over? Right, this is a big matrix. All right, so here, what do we know about Eij? Eij, every row is a zero except for the except for the ith row. Right? So only when C is I, it gives you something. Okay? C has to equal to I. So here this is negative. Now row I of Eij is actually little ej transpose. So yeah, let me get that matrix here. So Ij 1. Right. Okay. So the ith row of this Eij is exactly a vector that's having 1 at the jth element, and it's a row vector. And now we have column J, excuse me, column I of the matrix right here. But now let me write that column I as the following. Okay. So if I want to get that ith column, I just multiply by EI on the right. Okay. So now what do I have? I actually have what? I have actually, so this is picking, so this part is picking up the ith column, and this is picking up the jth row. So that's what? That's actually the element at the jth row ith column. So this is negative X inverse B A transpose X inverse jth row ith column. So this is what we want. So we started with the ith row jth column element, but now we notice, okay, we actually get the jth row ith column element. So that tells you what? It tells you the matrix that we want from here and the matrix from here, they are transposed to each other. Okay. So here, the left hand side from the previous long chain of equations, this is the ith row, j's column element, right? But now this equals to the negative of the right hand side is the jth row ith column element. That tells you what? That tells you the left hand side and the right hand side, they are transposed to each other. Okay. Yeah, okay, let me still keep that equation at the top. So now if you want to write the transpose of the product, that's actually going from the right hand side to the left hand side, taking the transpose of every part. Negative x inverse transpose, A transpose is A, B transpose is B transpose, X inverse transpose again. And exactly what we wanted. Okay. So this process is definitely what it's long, but it's not so bad. So I think actually one homework question from the book is can be done by doing this process. Of course, if you just do let me think. Yeah. So maybe the swapping is not required for the process, but it helps you to somehow isolate and get the part that you want. Okay. But yeah. So one of the questions is like the trace of ax b, and then ask you to compute the trace of ax b. They want you to compute the partial derivative. Okay, so for that, it's highly related to this one. So which is why in the homework I also made another question that's really similar to this. Okay, so remark. So del x of the transpose of xa equals to A transpose as a homework. Okay, so if you look at the dimension, so for any matrix X, let's say n by n, okay, then here in order for the trace to make sense, this XA, the entire product must be n by n. So A has to be n by n. Okay, and now if you think about the dimension, X has the dimension n by n. So this is 1 by n by n, of course, it's just the same dimension as X. Okay, but now if you look at A has n by n, which is the swapping of the dimension. So A transpose is matching with the dimension of the matrix as well. Okay, and the argument is gonna be really similar to what we established earlier. Wait, this is equation 5.103. Yeah. Right. Question? Yeah, so somehow if you look at this process, see exactly in linear algebra, it's there isn't really a lot about the partial derivative here, but essentially, yeah, well, for computing the gradients involving matrices, it's really about what's going on with the linear algebra for the computations. It's not really about partials. But of course, when you are doing the product rule, you need to make sure that the order of multiplication doesn't change. Because that really matters. Okay. The next one. Actually, we have two. We have 5.104 and 5.105. They are actually you can say the same thing. So when you have X transpose A vectors, doing the partial with X, that's the same as the partial of A transpose X, which is just A transpose. This is really straightforward, so we will not do it. But for X A, that's let's say n-dimensional. Okay. Oh, one thing I like to emphasize is that this is a scalar. Okay, X transpose A transpose X. This is a scalar. X is a vector, so the gradient here is just a row vector of the same dimension as X. But that transpose is a relatively common issue in your previous homework. Right. The next one, 5.106. We have X transpose, excuse me, A transpose X. X is a matrix, that's cap X. B, doing the partial with respect to X. Okay. This equals to AB transpose. So if you look at this is relatively similar to the one before 103. Okay, so 103 has A transpose X inverse B. Here this is A transpose XB. So yeah, let's do this all together. So the difference here is that X is a inverse. There's an inverse, so X has to be square, but this X doesn't have to be square. So if you think about the dimension, you could say this is n by n. B is n by 1. A is m by 1, so A transpose is 1 by m. Okay. So this is a scalar in the function that in the output. X is n by n as the input, and then you see AB transpose is n by n also. Okay. All right. Now a short proof. So it's a matrix. So let's do it by still looking at the partial with respect to Xij. Okay. So A transpose X B. So once again, it's a scalar. So we know the scalar equals to its transpose. A transpose XB. And realize that now we can swap the order. We can put the first block at the end. So it's XB A transpose. Okay. And once again, the trace is a sum. So I can swap the order. I can first do the partial, then do the trace. So it's the partial of XB A transpose. Okay. So first trace is well, excuse me. First do the partial, then trace. And now I have a product X times a constant matrix. So as you have seen before, if you apply the product rule, you will just get the partial of the first multiplying by the second. So this is the trace of the partial of X with respect to Xij. Okay, ith row J's column element B A transpose. Okay. Let me put the bracket right here because this is a product that you need to do first. And now at this point, it's going to be the exact same set as before. So del Xij is exactly EIJ that we established earlier. Okay, so only that ith row j's column element is changing, nothing else is changing. So now the trace that you realize, okay, you have a sum where C, the index goes from 1 through so let me think. So x is n by n. So this is n by n. This is n by n. N by m. So C goes from 1 through m. Row C of EIJ. And column C of BA transpose. Well, it's really like a repetition of before. Okay? So row C of EIJ. So only when C equals to I give you something. Okay. So that's row I of EIJ times column I of BA transpose. And that is EJ transpose, column I of BA transpose. So now we have column I of BI transpose, and now I'm picking up the jth row. Okay. So this is BA transpose JI. So once again, we realize, okay, I have the ith row jth element that I'm looking for in the resulting matrix. But now I end up with BA transpose, a constant matrix, taking the jth row ith column. Okay, so this is the transpose relationship. So in that matrix, I take the ith row jth column element, I get BA transpose. This matrix taking the jth row ith column. So which means the entire matrix is these two matrices are transposed to each other. Okay, so that's the relationship here. So that's BA transpose, whole thing transpose, which is a B transpose. All right. Question? So of course, for that homo question I just mentioned, this process is still true. So yeah, just realize that it's really it's something like this. Okay. So for the trace of x times a, that's something like this. So you do the partial from this step, and then pretty much everything just carries through. Okay, all the way to this point. So basically, that BA transpose doesn't change at all, starting from this point. Okay, so that's what you may find helpful for that homework question that I just mentioned. All right, we have what? We have two more equations, and they are not really complicated. So instead of doing them, let me just write down the equations, and I will fill out the details for the steps. But 5.107, that equation is the following. So we have x as a vector, bx. So this is a scalar, b transpose, x transpose bx. Okay. So this is n by n. This is n by 1. So 1 by n. So this is 1 by 1. So del x as a vector. So this gives you x transpose b plus b transpose. And 5.108, it's a really similar result. So now this is a vector x, but now let's say my argument is a little s. Okay, so not
Same thing as before, just with the square matrix, right?
really wait. A little bit different. The difference is the following. So that is a matrix in the middle. Here we're just doing the partial with respect to these. So 107 is much simpler than 106 in a sense. Let me write down 108, and we probably have the time to just go over this computation. So x minus as transpose w x minus as. This equals to, so 107 and 108 are highly related, really similar. However, the difference here is that this is a vector, this is a vector, but now S in the front is A, this is a matrix of multiplication. Okay, so S is still a vector, but now there's an A, so it will be a little bit different. So the result is x minus AS transpose WA. Okay, so W here is symmetric. So if you have a symmetric W, then the gradient is something like this, kind of quadratic. Yeah, so let's quickly do 107 and be done for today's class. So here is a vector, right? So x is a vector. So we eventually want to get a vector. So del x transpose bx, doing the partial with respect to, let's say, xi. So this equals to, so here is a product, right? We have x transpose bx. So we say, okay, we have x transpose as the first function, bx is the second function. So it's the partial of the first times the second plus the first times the partial of the second. Right? So now what do we have? So x transpose is a row vector. I'm doing the partial with respect to xi. So let's just give you the EI transpose. Bx. Okay. And now for the second one, just realize that bx, right? So it's again the product. So I can just do the it's just b times del x del xi. Still matrix multiplication, so it doesn't change you much. But this is what this is just EI. Okay. So now let's just put the things put the EIs all together. So this is here we have EI transpose BX, right? So that you can say that's BX whole thing transpose EI plus X transpose B EI. Okay. So I can rewrite it as what? I can rewrite it as X transpose B transpose plus X transpose B times EI. And done.